So, hello everyone. We are Group 4 and we will now discuss the problems relating regenerative Rankine cycle. So, problem number 1. A steam power plant operates on an ideal regenerative Rankine cycle with two open feed water heaters. Steam enters the turbine at 8 MPa and 550 degrees Celsius and exhausts to the condenser at 10 kPa. Steam is extracted from the turbine at zero point 0.6 and zero point 0.2 MPa. Water leaves both feedwater heaters as a saturated liquid. The mass flow rate of steam through the boiler is 16 kilograms per second. Show the cycle on a TS diagram and determine A, the net power output of the power plant, and B, the thermal efficiency cycle. So this is the TS diagram. As we can see that there are states which we can call isobaric process since they have both uh, pressures such as at pressure 1 and 10, which is 10 kPa, and pressure, I mean, state 2 and state 3 and 9, which are 200 kPa or zero point 0.2 MPa, and state 4, state 5, and state 8, which is 600 kPa or zero point 0.6 MPa, and state, state, state 6 and state 7, which are 8,000 kPa or 8 MPa. So next slide, please. So in here, we can see that we can now get the pressures since we can see it in the TS diagram, the isobaric processes in each states, and also for the isentropic process. Also, you can also see it in the TS diagram. So the isentropic processes are the state 1 and state 2. So they have the same entropy value. State 3 and state 4, they also have the same entropy value. State 4 and state 5 and state 6, they also have the same entropy value. And also for state 7 to state 10, these four states, they also have the same entropy. So with this, we can now get the enthalpy values of each state. So we can see here in the table. So first of all, we need to get the y and z values. These are the uh, steam exhausted. So first, we need to have um, the formula, which is the uh, summation of energy input is equals to summation of energy output. So in here, under energy input, we have the state 8, state 4. So we have the enthalpy values of this state. And as for energy output, we only have our state 5. So the formula for getting the y value is my h8 plus m times 1 minus y h4 is equals to m h5. And divide this equation by m. So we can now have the equation which is y times the enthalpy value of h8 plus 1 minus y times the enthalpy value of h4 and which is equals to the enthalpy of h5. And with this, we can now get our y value, which is 0.0717. And next, we need to get the z value. So we also need to get, we also need to have this formula is the summation of energy input is equals to summation of energy output. So M9, H9 plus M2, H2, these are the energy input. I mean, these are the components under energy input. And under energy output, we only have state 3 or M3H3. And divide this value by M, we can now get this equation, which is Z times the enthalpy value of state 9 plus 1 minus Y, the value we get under, I mean, the value we get in Y minus Z times the enthalpy value under state 2, and which is equals to uh, 1 minus Y times the enthalpy value of H3. And with this, we can now get our Z value, which is 0.1201. So next slide, please. So now we have our Y and Z values. We can now solve for our work pump. We also need to have um, the formula, which is the summation of energy input equals to summation of energy output. So under energy input, we only have the state 1, state 3, and state 5, and also the work pump itself. So we can see here that we have M1 H1 plus M3 H3 plus M5 H5, and the work pump itself. And under energy output, we have state 2, state 4, and state 6. So we can see here that we have M2H2 plus M4H4 and plus M6H6. So the working formula for our work pump is equals to M2H2 plus M4H4 plus M6H6 minus M1H1 minus M3H3 minus M5H5. And plugging in these values, so values we get from the table under enthalpy value. So under H2 we have 192, under H4 we have 505.14, under H6 we have 678.50, under H1 we have 191.81, under H3 we have 504.7, and under H5 we have 670.38. So each state, they have each corresponding mass flow rate formula. As we can see here that under H2, it has the formula of M times 1 minus Y minus Z. And under H4, it has M times 1 minus Y. And under H6, it has only M. I forgot to put M here. So it's supposed to be, it has M here. So 678.50 M. And under H1, it has M times Y 1 minus Y minus Z. Under H3, it has M times 1 minus Y. And under H5, it has M value only, same as this H6. So divide this equation by M. We can now get our work pump, which is 8.682 kilojoules per kilograms. And we also need to get our work turbine, since it is needed for our work net formula. So getting the work turbine, we also need its formula, which is the summation of energy input equals to summation of energy output. So under energy input, we only have state 7, while under energy output, we have work turbine itself, state 8, state 9, and state 10. So the working formula for our work turbine is equals to M7H7 minus M8H8 minus M9H9 minus M10H10. And as what I have said earlier, that each state has its corresponding mass flow rate formula. So under H7, H7 it has only uh, its enthalpy value, while for H8 it has um, my, so mass times y, and under H9 it has mz, and under H10 it has m times y, m times 1 minus y minus z. So divide this equation by m, we can now solve for our work turbine. And we also need to plug in the values we get under under y and z values. So now we have our work turbine, which is 1,245.850 kilojoules per kilogram. So now we have our work turbine and work pump. We can now solve for our work net. So the working formula for work net is equals to mass flow rate times work turbine minus work pump. So we have our mass flow rate, which is 16 kilograms per second, and our work turbine, which is 1,245.850 kilojoules per kilogram, minus the work pump, which is 8.682 kilojoules per kilogram. So the work net now is 19,794.690 kilojoules per second. But we need this unit in megawatts, so we need to multiply this by 1 over 1,000. So our work net now is 19.8 megawatts. As for the thermal efficiency, Mr. Gallego will report this. So
Okay. Moving on to the next required parameter, which is the thermal efficiency. We can solve this by using these two equations, namely net work over the energy input at the boiler, or what we can use 1 minus the energy output at the turbine over the energy input at the boiler. Now, since we solved already the network, we can use the first expression, which is the network over the energy input at the boiler. Now, since the expression needs the network and the energy input at the boiler, and we don't have the value for the energy input pa, so we will solve the energy input, and it's displayed in the slide. Now, by solving for the energy input, we need to do an energy balance at the boiler. So we'll have energy input on the left side of the equal sign is M6H6 plus the energy input is equal to um, the expressions that are leaving is M7H7. Now, M6 is equal to M7, and they're only M, the kanang mass flow rate is only M, because there are no fractions at this point of the analysis. Now, dividing the expression by M, we'll get uh, energy input is equal to the quantity H7 minus H6. And we solved already for these and enthalpies. So we have H7 is 3521.8, and our H6 is equal to 678.50. Now plugging in, we have the energy input at the boiler is equal to 2,843.3 kilojoules per kilogram. Now substituting the values, we have the known values already. We have the thermal efficiency is equal to the network over the energy input at the boiler, which are 19,794.690 kilojoules per kilojoules per second rather, over 2,843.3 kilojoules per kilogram. Will have and multiplying the denominator by 16 kilogram per second per the, because we have the given mass flow rate. So our thermal efficiency now will be 0.4351, or in percentage we have 43.5%.
The next is problem number 2. Consider a regenerative vapor power cycle with one open feed water heater. Steam enters the turbine at 8.0 MPa, 480 degrees, and expands to 0.7 MPa, where some of the steam is extracted and diverted to the open feedwater heater operating at 0.7 MPa. The remaining steam expands through the second stage turbine to the condenser pressure of 0.008 MPa. Such saturated liquid exits the open feedwater heater at 0.7 MPa. The isentropic efficiency of each turbine stage is 85%, and each pump operates isentropically if the net power output of the cycle is 100 megawatt. Determine the thermal efficiency and the mass flow rate of steam entering the first turbine stage in kilograms per hour.
Okay, so for the first step of this solution for problem number 2, we have the TS diagram and the given values. So you might have noticed the TS diagram has different notations for the different points. So point 1 is the point where steam enters the turbine. Point 2 is after the first stage turbine, and so on and so forth. So here we have our given data on the pressures. So some points, some processes, some points are isobaric, so they have similar pressure, and net power output is given. So for now, from the table, we have to get first the entropy and the enthalpy of the state as it enters the boiler. So from the table, from the steam table, here we have H1 is 3,348.4 kilojoules per kilogram, and its entropy is 6.6586 kilojoules per kilogram at zero point 0.7 megapascals, which is after the first stage turbine. So that's zero point 0.2. So we have these values, and at 0.008, which is the condenser pressure. So we have these values. All these values are taken from the steam table. So first, solving for H2, we get 3,348.4 minus 0.85, 3,000, multiplied by the quantity of 3,348.4 minus 2,740.78. So if you're wondering where this formula came from, this formula it was uh, derived from the isentropic efficiency of the turbine. So we got 85% here, and then we move the variables around so that we'll be able to get H2 using uh, H3 and the H2 from the table. So H2 here stands for the actual and enthalpy of the turbine, and yeah, and for the other one, the isentropic one, we'll be using a subscript of S, so this will be H2S. So H2 here is the actual enthalpy, and we get this value. Then from the separated table, again from the table, the entropy is this value, 6.8588 kilojoules per kilogram. And here, as we know that uh, process 2 and process 3, so before and after the second stage turbine, they are isentropic. So we can use that to solve for the enthalpy of the third state. So first we get the quality. Here we get the quality of the third state, which is at 0.82. Then we plug in the values in solving for the quality using the enthalpy formula, which is the H we're looking for is equal to HF plus the quality, then HFG, or HGF rather, which is basically HG minus H4. So we plug in the values and we get H3S, which is the isentropic enthalpy without the actual irreversibilities yet of the third state at 2,144.43 kilojoules per kilogram. And then again, we use the isentropic efficiency formula of 85% is equal to um, the actual work over the isentropic work to get the actual value of H3. And there we plug in the values and we have 2,247.517 kilojoules per kilogram. Next, we solve for the pump work. So first, we get H5 since the pump has no irreversibilities. With H5 is just H5 as it is. So getting H5, we have this 174.577 kilojoules per kilogram. So H5 is this will be the state after the first pump, and this is the work. No, wait. Yes. This will lead us to the work of the first pump. Then the work of the second pump will involve state 6 and 7. So first getting state 7, we get this 705.358 kilojoules per kilogram. But before all that, since we have steam that fractures off into the feed water and into the second state turbine, we have to take into account the amount of steam that diverges, the fraction of steam, and that's y. So solving for y, um, we use this formula, y equals h6 minus h5 over h2 minus h5, and we plug in the values. We get y, the fraction of steam that fractures off, is equal to 0.196. So next, we solve for the total turbine work. Uh, we plug in the values so we get the work of the first turbine plus the work of the second turbine. And as you can see here, there's 1 minus 0.196 to indicate the fraction of steam that was going to the second turbine. So the turbine work is 986.296 kilojoules per kilogram. And for the total pump work, we add the first and second pump works. So we get 8.835 kilojoules per kilogram. So this is, yes, basically the previous one, but I apologize for not having it here. And then for the network, we get the work of the turbine minus the work of the pump. We get 977.461 kilojoules per kilogram. Q supplied or Q in is H1, the state after the boiler, minus H7, the state before the boiler. We're solving for that. We get 2,643.042 kilojoules per kilogram. And now we have everything we need to solve for both questions. So for thermal efficiency, it's basically the net work done over the energy or the heat that comes in. So it was the last things that we solved. So we get, plugging the values in, we get a thermal efficiency of 0.3698 or 36.98%. And for letter B, the mass flow rate of steam entering the first stage turbine. So we get the net power. So here we be using this formula. Net power is equal to the mass flow rate times the network. So the mass flow rate would be equal to this 102.3 kilograms per second, but it's asking for it in kilograms hour. So we'll be multiplying it by 3600 seconds to get it in kilograms hour. So the final answer will be this one, 368,301.14 kilograms per hour. Here will be our final answers. And that's all for today. Thank you.